Welcome guys, grade 12 IEB matric students. So we're here today with Megs and Phil and we are doing some chemistry. So it's paper 2, right?
Absolutely.
Paper 2. So Mr. Phil, introduce what we're doing. Tell us all about it.
Okay, well guys, what we're going to be doing is we're going to be taking apart some of last year's toughest questions out of the IEB paper.
Oh, that's
So
my...
yeah?
Oh, this is terrible.
There we go. This is going to be like a flashback for you.
I just had a click of me in that chemistry exam going, oh my gosh. But anyway, let me tell you what's happening with the Samsung competition. So it's the Learn Extra Exam Revision Marathon competition. Because you know, you're running a marathon because you guys are finished in like a week and a half. And then you know what time it is. You guys know. So then, while I'm telling you about that, you guys have to be studying now or just at least revising. Because let's face it, tomorrow it's a tough day, believe me. It's hectic. So, Samsung, you guys can win the Galaxy Note 10. Oh, look at it in all its glory. Do you see this beautiful device? Yes, it could be yours. Mine said it's easy peasy. All you have to do is download the notes, enter the race number, which is at the bottom, so it'll be A and 4 digits after that, and you enter it into the competition link that I will be posting on Facebook. And how to get hold of me and Phil, it's facebook.com/learn extra. So I think that's all of my Samsung sponsored competition, so I think it's over to you, Phil.
Thanks so much, Meg. Okay. Well, as I said today, we're going to be taking a look at some of the toughest IEB questions from last year. And there's some really nice ones because they cover the things which are specific to the IEB exams. Now, you'll notice that some of the government papers or the DBE papers are slightly different in focus. This lesson is going to focus on the things which you won't find in some of those papers. So, I mean, just on the menu is very, very specific today. We're just going to be dealing with those exam questions. I'm going to be showing you what to watch out for, showing you some of the important steps, and some of the stuff that is really, really important and is likely to come up tomorrow. Okay, so by no means make this your only focus of study this evening. Guys, this is just to fill in the gaps of knowledge. Now, I noticed a lot of textbooks don't give a lot of time to these types of questions, so that's what we're going to do today. This is not a replacement for your studying, guys. Okay, so now this particular one I picked out of last year's paper because it started to talk about the aluminium process and talking about the Kastner-Kellner process, which produces aluminium. Now, the reason that they love this process so much is because South Africa produces a large amount of aluminium out of Richards Bay, and in Mozambique it's also produced in Maputo. So it's a very, very important process. We export a large amount of aluminium. Okay, so here we go. We've got sodium aluminium hexafluoride. Now that's a real mouthful. And you probably don't actually know this chemical name because it's never been taught to you directly. However, you might know this name, cryolite. Okay, now cryolite is a very special chemical. You do need to link it up with the formula. So there's 3 sodiums, 1 aluminium, and 6 fluorines on there. So that's sodium aluminium fluorate. Okay, so what we've got here, the common name is cryolite. Okay, and it's added to aluminium oxide or alumina. Okay, just a reminder that alumina is Al2O3. Okay, now that's the very pure form of aluminium oxide. This is what you need to put into the process. Now, you might know that aluminium oxide goes by a different name when you dig it out the ground. The mineral's name is bauxite. B-A-U-X-I-T-E. Bauxite is the raw material which you use to get alumina. Alumina is a very pure version of aluminium oxide. Now, your cryolite and your alumina both go into that melting pot and something very special happens there. Now, there's a reason that I use cryolite, and it's not because it's got aluminium inside it. It does something very specific. So guys, what I'm going to do is I'm going to discuss what cryolite actually does. It says, what is the reason for adding cryolite to the reaction mixture? So why do I put this very expensive, very toxic chemical inside there? Well, let's look at our options. So option A says it prevents the graphite electrodes from corroding due to the large electric current being passed through the electrodes. Okay, well, guys, there's some truth in every single one of these answers, and they're all going to seem like they look right. They are really trying to find out if you really know what you're doing. Now, option A, I can see a lot of people saying, oh, well, that sounds legitimate. Now, it says it prevents the graphite. Oh, this all sounds right, but cryolite, that's not its job. Option A is not correct. Yes, the graphite electrodes do corrode. Now, that's not cryolite's function. It's not to protect them. even though they do corrode, and I'll tell you a little bit later on why, if we've got a little bit of time, but that's not the right option. So option A is out of the box. What about option B? It says it helps reduce the melting point of the alumina. Okay, now if you've studied very, very carefully, you'll notice that that is exactly what alumina is designed to do. Alumina drops in melting point from 2000 degrees, which is hotter than the melting point of steel, down to around about 900 degrees, which you can actually manage relatively easily. Can't hold it in your hands, but you can put it inside a steel pot, and that's really important. If I can't put it inside a metal pot, it's just going to melt out the side. It's very difficult to contain and hugely expensive. Here we go. So it reduces the electrical costs of keeping the aluminum molten. Okay, absolutely. So option B looks like our best choice. But as always, Matrix, consider all of your options before settling on an answer. Then you can see if you're right, even if it's just by a process of elimination. Okay, so option C over here, let's take a look at option C. It says it acts as a protective layer to protect the iron container. Wait a minute. That kind of sounds legitimate as well. Protect the iron container. Well, you've got lots of hot molten alumina and aluminium. The iron container must be protected, but this is not the material which does it. There's two layers of protection between your alumina and your metal pot, your aluminium containing pot. Now, you do have an iron container around the outside, but inside that there's a layer of very, very high temperature bricks, and then there's a layer of graphite as well. So there's two layers of protection for the iron. But it's not cryolite. So option C, again, is out. Now D, it says it acts as a catalyst. Oh, wait a minute. Now this sounds like it might help. Very often I might throw a material into something and that helps me in terms of getting my reaction to go a little bit faster, and this seems to be something which might be correct. But now what we find out is that cryolite is not actually a catalyst. All that it does is changes the physical properties of alumina, not the chemical properties. D sounded correct, but it wasn't actually, and that leads us back to option B. And I want you guys to get on the Facebook page here, start interacting with us, and start sharing your answers. Why do you think it was one option, not the other? Guys, it's all about sharing these answers. Okay, so aluminium process, something likely to come up. So this is something that you won't see in the DBE papers. It's a really nice application of electrolysis. Okay, let's move along. Okay, so now this particular question I like a lot, and this is one of the reasons that I picked it out, because it's super, super, super tricky. Now, it says that you've got to start dealing with certain things like monomers and polymers, and this particular one is a super tricky question. It says the monomer, and that's a bit of a weird word. Okay, monomer just means that it's a single piece of a larger chain. So it says the monomer of chloroethane, and we've got it drawn down at the bottom there. Sometimes it's called vinyl chloride. Now in industry it's called vinyl chloride, but the correct IUPAC name for it is chloroethene. Now, the fact that it's chloroethene tells me that this is going to make an addition reaction. So it's an addition polymer. That's what alkenes will be doing when they start to make up a polymer. Okay, so alkenes are responsible for addition polymers. That's the giveaway that we're going to do, addition polymerization. Okay, so lots of long fancy words. Let's see what the rest mean. Okay, so it says it polymerizes, okay, to form the polymer polychloroethene, which has got a different name. In fact, I'm busy giving away some of the answers there. Okay, so it says polychloroethene, which I don't really recognize all that well, but there's another trade name for it, and it's going to come up a little bit later on. You might even recognize the name for yourself. So it says by means of addition polymerization. Okay, so that's as we predicted. Addition polymerization is a three-step process where step one is initiated. Now, initiation is usually the start of something, okay, by a free radical, and this is represented by the symbol R with a little dot next to it. Okay, so here we've got our chloroethene. It's a molecule which is ready to add to everything else. We're going to make a polymer out of this in various steps, but first we've got to answer some of the grunt questions, some of the theory questions. And I want you guys to start debating this, because polymerization is one of the most difficult sections in organic chemistry, and it's something which gets a lot of people really stuck, and it's not really necessary for them to get stuck. Okay, so let's discuss the most basic terminology that we've got. What is meant by the term free radical? Okay, now there's a couple of things which make a free radical. Free radicals have got a single unpaired and unbonded electron. Okay, so how do I write this thing out? And let's see if we can see this unpaired electron. We've got R, which has got that unpaired electron. This is what makes a free radical. It's an unpaired and unbonded electron. Okay, so guys, it's an electron which is looking for a friend. Okay, it hasn't bonded yet, but it's going to. And let's see how this can start the whole process. Now, let me give you a little bit of a hint as to where we're going with this question. Don't forget, when you start drawing your monomers, in other words, your double bonded monomer, there's a little bit of a trick that I want to show you guys, and I'm going to redraw it in a very special way. Now, if you've got your C double bonded C ready to do addition, I want you to get away the other things which are actually in the way of polymerization, and they're going to help you draw the correct polymer. I want you to change the bond angles very slightly. Now, this is not how they actually look, but it's going to help us in terms of just getting these things in the right way. Now, I noticed a lot of people put the chlorine flat. Please don't, because then the chlorine's going to get involved in the polymerization, and that's not correct. So we've got these hydrogens, we've got these chlorines, we've got the double bond, we can start our polymerization reaction. But there's always something else which I want to tell you guys. Never forget the following: that a bond between two atoms is just a pair of electrons waiting to be unclipped. Specifically, these two electrons. So we could replace this line with a double dot. Now, why am I telling you about dots? Well, there's a dot which is on the radical. The radical wants one of those dots to make a bond. And that's what we're going to do in the coming steps. Okay, so now that we've discussed some of these fancy words in the original question, let's start taking a look at what the rest of the question says. Okay, so it says, name the other steps in the addition polymerization process. Okay, well, it says the other two steps. Okay, so two other steps in the addition polymerization process. Well, we've already done, or at least discussed, initiation, which is the beginning of polymerization. There's two more steps. Step 2 is called propagation. Okay, so propagation is what happens after we've started everything else. Now, propagation is probably the longest section of polymerization because it's where the chain is growing and growing and growing and putting on more monomers. So propagation is the growth phase. And then at the very, very end of polymerization, a really fancy way to say the end is termination. Termination is when addition polymerization comes to an end. Either you've run out of monomers or two radicals have joined each other. We'll discuss it later if we have time. Okay, so there's termination. So termination is a really important step, obviously, because the polymerization is going to come to a halt for many reasons. Now, this is the part which I'm going to prime you for. And I want you guys, even if you can start sharing pictures on the Facebook page, I want to see how you guys draw this out. Now, it says, using the structural formula of chloroethene, that's my monomer, given, show how a monomer of chloroethene reacts with the free radical, okay, in the initiation step. So let's take a look at our free radical. There it is. I've got my free radical. And I've got my monomer, which is waiting to react. Now it says that I've got to use these two formula to show how a monomer reacts with the free radical in the initiation step. Okay, so let me get you set up for how to do this. Now, remember that a double bond is nothing more than a collection of 4 electrons. Now, I've just highlighted the one bond which is going to break. Remember what happens in addition. Addition is the breaking of one of those double bonds, and then it's going to make another bond with something else. And in this case, it's a radical. Remember that a radical is looking for a friend. Now, what happens is we get movement of electrons. Now, this radical really likes the electrons between there. In fact, it's going to grab one. And the way that we show that is it wants to make a bond with the carbon. So it's going to donate its electron into the bond, and I use a half-headed arrow to show that. Then one of these electrons is going to come out to meet it and complete the bond. two electrons meeting each other and making friends is going to make a bond. Now, what you've got to realize is that there's a carbon at the end there without another bonded electron. Guys, I want you to make some suggestions as to where that electron is going to find itself. But first, I'm going to give you a little bit of time to discuss this, maybe chat on the page, and we're going to take a look and see what people's answers are. How about that, Megs?
Cool, Phil. Well, Onche says I must give her a shout out, so shout out goes to you. Hope you guys have a good ad break, but don't go too far because we'll see you afterwards, okay? Welcome back, guys. So my producer / other director came into me and was like, why didn't you announce Curio? So, bad Megan. So, you know what the challenge is, right? No? Maybe? Okay, well, I'm going to tell you anyway. Curio is only for you, Matrix. So how it works is that you register on www.curio.co.za. Okay. Then there's questions for you to answer. So whoever answers questions the quickest and the most correct get a 100 Rand airtime voucher. I could use a 100 Rand airtime voucher. So I think you guys should actually enter, and the code or the passcode that you enter is PS12.
Makes sense.
Physical Science 12. Anyway, so that's how it works. And then the winner will be announced before the end of the show. So get in, get registering, get doing the questions because we want to see how much you guys know. But I have to give a shout out to Anati Toti. I hope I said Toiti, or I hope I said it right. She says, hey Megs, can you shout out to me and my aunt Linda? She enjoys watching Learn Extra with me. So a big shout out to you guys. And Linda, I'm so proud of you for watching with your niece. So, Phil, are we ready to carry on with free radicals?
Absolutely, absolutely.
Awesome.
Guys.
Let's go.
Okay, well, guys, before the break, I posed to you the question, what happens when a free radical approaches a double bond? Okay, now a free radical is out for electrons. It wants to grab an electron. So what it's going to do is it's going to see that double bond and say, I like those electrons. It's going to take one, and it's actually going to break the double bond. So radicals will break the double bond. Now what I'm going to do is I'm going to draw the product with you. So let's do exactly that. So my product, so if I draw a little arrow here to draw the product, my product won't have a double bond anymore. It's going to have a single bond. Now this is the other magic thing that's happened. The radical has now bonded to that carbon over there, and what I'm going to find is that chlorine has gone along for the ride. Guys, please don't get confused and start putting radicals and things on the side atoms like chlorines or methyls or whatever might be the case. Guys, the chlorine doesn't get involved. It's just along for the ride. Okay, so here we go. We've broken the double bond, but there's something not quite right. You'll notice that the carbon on the right-hand side of the picture is missing an electron. Now, that's what happened. Inside this breaking of the double bond, what you'll notice is that this carbon takes back its electron and it's going to wait for some more friends. It's going to make a new radical. So there we go. What I do is I represent that radical with a single dot. That dot is waiting to make a new bond. Okay, so now in this next part of the question, it's going to ask me to do something with that. So it says, show how chloroethene polymerizes into PVC. Guys, PVC, I think I've heard of that before because PVC is going to be used in all sorts of industries. Now, guys, every single one of you has touched PVC at least today because PVC is all around you. It's used for almost every plastic good around there. It's a really nice, cheap, hard, durable plastic, and it's used from laptop computers. It's used to waste pipes. It's used to, you'll actually find it everywhere. Some TVs have got it built around the side. We'll discuss that later, though. Now, we've got to do step 2. Now, step 2, remember, was propagation, where the chain grew. Now, it says, use 1 repeat unit in your answer. Okay, so now, how am I going to grow the chain? Just a reminder that I've started my chain. So my chain started with 1 monomer and a chlorine along for the ride. Okay, now, remember that we've still got a radical on this last carbon. Now, what did I tell you about radicals? Radicals are in it for the electrons. They want to grab an electron anywhere they can find it. So where's the best place to grab more electrons? Well, guys, if you're guessing it's another monomer, you'd be absolutely correct. Now, I'm going to give you a little bit of a tip here. Draw these 2 carbons with the double bonds and everything else to the top and bottom. Get them out of the way. So here we go. I've got another monomer lined up, ready to make a chain of PVC. Now, propagation says, adding on more monomers makes my chain longer. So I've got a free radical. This kind of looks familiar because it's exactly the same as the last step. If you know how to put together a radical and a double bond, and I do, so there we go, a radical donates its electron, the double bond donates the other electron, and they make a bond between the two of them. Then we get the carbon, which takes its electron for itself. Now let's draw that product together. So what I'm going to do is I'm going to switch to the original colors, and we're going to see where all of these pieces went. Okay, so what happens is I've still got my R, carbon, carbon, chlorine that came along for the ride, all the hydrogens. Don't forget the hydrogens because you will lose marks. Okay, now I've got a new bond. So here we go, my new bond, which is formed over there. 2 carbon chain which has been added on with the chlorine on top. Notice how the entire thing has come along. We've broken the double bond, but don't forget, there's still a radical on the end. And you can see that this can happen again and again and again and again. All you need to do is keep on adding that double bonded carbon, keep on adding them on, and your radical will break open the double bond and make a new radical. Break open a double bond, make a new radical. This is how addition polymerization goes. There was a question on the page a little bit. You said that there was a question about addition, substitution.
Yeah, I wish I could find, I'm just posting something.
I think I remember it.
Okay, go for it.
Okay. Well, somebody on the page was asking, what's the difference between addition and substitution, if I remember it correctly?
Yes, exactly that.
Okay. Now, how do I know that the reactions on the board here are addition reactions? Well, guys, here it goes. Probably the simplest way that you can tell is that your reactant is unsaturated, meaning that it's got double bonds between it. What happens during an addition reaction is I break double bonds. Now, you can do it to triple bonds as well, but you've always got an unsaturated reactant in there which breaks open one of the double bonds. That is the telltale sign that you've got addition happening. Now, addition will always result in a more saturated product, meaning that there should only be single bonds. And if you look at the product, I only see single carbon-carbon bonds. So this proves that I've got an addition reaction going on. I hope that you can see where these pieces came from. I had monomer number 1, monomer number 2, and they joined, and all you have to do is keep on joining the monomers. Now, how do we end off one of these? Well, guys, I'm going to leave it to you. You can do something with that end radical. If 2 radicals come together, remember that they can make a bond. So if I get 2 radicals coming together, that actually stops my polymerization. If I keep making more radicals, the reactions are going to keep on going. And this is how they make plastics. Okay, so let's carry on with these questions. Okay, now vinyl chloride, which remember is our monomer, is a chemical intermediate. Okay, that means that it's not the final product. It's incredibly hazardous, and generally, guys, you want to stay away from vinyl chloride. It's highly, highly carcinogenic, which means that it causes cancer. Okay, so vinyl chloride is really not nice stuff, but what they do is that they don't use it in any end product. So you won't find vinyl chloride in your shampoo for obvious reasons. However, that's just the monomer form of this chemical. Something really magical happens when you make polyvinyl chloride. When you just join together enough of these monomers, you change the chemical and the physical structure of this material. Okay, it's very stable, it's very storable, and it's nowhere near as acutely hazardous as the monomer. Now, that's a really fancy way of saying the stuff is safe. In fact, I would go so far as to say you can actually eat PVC. It's
what?
not going to do... Yeah,
no.
Okay, it's not going to be a very pleasant experience, and it's probably not the best idea for your stomach. But look, I mean, matrix, don't go out there and grab a pipe and start munching down.
Please don't.
Okay.
Or bottle or something.
Okay, but PVC itself is actually relatively harmless because it's completely inert. In fact, this is one of PVC's biggest problems. It doesn't break down. Your stomach acid and your enzymes in your stomach aren't going to do anything to PVC. It's just going to pass straight through. So guys, please, you know, it's not going to poison you, but please don't go munch PVC. Okay, you can eat it, but it doesn't mean it's a good idea.
We do not suggest that at home.
Okay, do not try this at home. Okay, so now based on its stability, storability, and non-toxicity, suggest 2 possibilities where PVC or polyvinyl chloride can be most effectively used in society. Okay, now guys, one of the most common uses for PVC, you'll actually notice this anytime there's any sort of plumbing which is exposed, even 99.9% of the toilets that I've looked behind, unless it's actually built into the wall, you'll actually see a white plastic pipe going out of the back of the toilet. The reason they use PVC is because that's going to stay intact. You don't want any of that stuff going in the bathroom, so you want to make sure that the plastic that you use is very, very durable, and it's going to be durable for as long as the house is there. Okay, so it's very, very effective in plumbing. Plumbing is very dependent on PVC pipes. Those really thick pipes that you see that are made of plastic, that carry wastewater specifically underneath sinks or the backs of toilets, you'll find that plumbing uses PVC very extensively. What you'll find is that PVC is actually very useful for stationery, pens, rulers. You'll actually find that a lot of the flexible plastics inside your pencil case or whatnot, so you can actually start to do, you can talk about pens or rulers, anything which is made out of plastic which you would like to be very durable. PVC is ideal for that. You don't want the pen that you very often nervously while you're studying chewing away at it. You don't want that to be a toxic substance. So PVC is an ideal candidate there. But again, please don't go munch down on some PVC. Okay, so that's it for that particular part of the PVC question. Now, we're going to start doing some redox chemistry. And a lot of you guys at home are not happy about
like me, I was like...
Okay, redox is the unhappy question for a lot of people.
Because you have to understand first what a redox reaction is, and then you need to like break it up.
But that's why we're here.
Yeah.
That's why we're here.
He's going to teach me all over again.
Oh, absolutely. Okay, second time around. For you guys, this should not be the first time that you've looked at redox. And please, I hope that this is not the first time. If it is, listen very, very closely and carefully. Okay, so we've got an experiment. Okay, so Vanessa decides to set up a silver copper galvanic cell. Now, a lot of you are going, ugh, all these big words, and you just start getting a headache just reading through this passage. So what we're going to start doing is we're going to start taking it apart. So silver, copper, galvanic, those are all really important. That means that Vanessa has managed to organize herself some silver and some copper, and she's arranged them in such a way that she's made a galvanic cell. Now, if you're making notes on this, a galvanic cell is a cell which takes chemicals and makes electricity, just like the batteries which you put inside torches or inside your cell phone. The whole idea is that I can change chemicals into electricity, and that's what Vanessa is hoping to do. Now, it says that she does this under standard conditions, and we'll discuss those as the question goes on. She's provided with a silver spoon. Okay, that's really nice. I want a silver spoon. And a small piece of flat copper plate. So she has both metals. So she's got a flat copper plate. So that's really important to notice. She's got a silver spoon and a flat copper plate. So she has silver metal and copper metal. And that's really important. When you start to take a look at your redox table, what you put on there is very, very important. She now places a silver spoon in a silver nitrate. Okay, that's really nice. She's put the metal inside a solution of silver nitrate. That means that there are silver ions.
Can I interrupt you for 2 seconds?
Absolutely.
A mindsetter said, you've got a beautiful name, Evangelist. Okay. I posted the question about 10 minutes ago so they could do it, and she just said that, I just wanted to know if she's right, that is a electrochemical cell, so if you know the C rule, then you're fine. So what is the C rule?
Okay, I'm going to show you what the C rule is, and to be careful when using the C rule.
Okay, well that's all she said. I just wanted to know what it was.
She is correct that this is an electrochemical cell, and the C deals with galvanic reactions, in other words, spontaneous reaction. So she is correct over there. Okay, I'm going to show you how to use the C correctly, but to be careful when using it.
Okay, cool.
Okay, so we've got a silver spoon dipped into some silver nitrate. We've got some copper, and we're told that the copper is placed in a copper sulfate solution. The two half cells are then connected to a small light bulb marked 1.1 volts, and a diagram of the cell is given below. Now, grade 12's pictures are your friends in exams because reading through all of that information makes my head hurt. And I'm pretty sure you're the same, that by the time you've reached the end, you've forgotten everything in the beginning. So what I recommend that you start doing is you read through your passage, you look at your picture. You go, oh, okay. Well, first, it told me that Vanessa had a silver spoon. Okay, there we go. We've got silver metal. That's great. Okay, so that doesn't look very much like a spoon, so we need to speak to the illustrators in the IEB. But, okay, we can see that this is AG. AG is silver. And the way that I remember that it's not gold, you say, no, it's not gold. Okay. So Ag, which is silver, okay, so we've got silver dipped in some Ag+. And the Ag plus we actually got from AgNO3, which is silver nitrate. Okay, so that's really nice. We've got our light bulb, which was marked 1.1 volts. And we've got a copper plate on this side with some copper ions. So copper plate, which is the metal, and some ions. I don't know if you can see that at home. So Cu2 plus, which came from CuSO4. And these are all of our reactants. You'll notice some other bits and pieces. There's something in the middle here which looks a little bit suspicious. It's marked item B. Okay, so now we can go and answer some of the questions inside here. Okay, now guys, it's almost time for an ad break, but before we go to the ad break, I like to post some questions and I want your answers on the page. What is meant by the following terms? Now, we've already discussed this, so I hope you've been listening. What is meant by the term galvanic cell and also standard conditions? So these two terms I want you to discuss on the page, share them with each other, and we're going to see what comes up.
Awesome, Phil. Thank you very much. But guys, think about it. Because in my exam last year, you get so confused in the moment that you get confused between galvanic and what's the other one?
Electrolytic.
There we go. I knew it. So just go quickly, have a little bit of a thought, and we'll be right back. And welcome back, grade 12. So the IEB matrix, you guys are writing chemistry tomorrow. I promise you it's nothing to stress about. There's no use cramming it in the last minute. So just watch Mindset and I promise everything will be smooth sailing. But don't forget about Curio, because you just have to answer a few questions in the quickest amount of time and hopefully they are really correct or the most correct. And then you get to win a 100 Rand voucher. So come on guys, please enter, because I want to say the name at the end and I want there to be lots of entries. So you register on www.curio.co.za and the passcode is PS12. So galvanic cells or standard conditions? I don't think anyone has answered me, and I'm upset.
Guys, you're a little bit slow on the page today.
I'm upset.
Okay, well guys, let's jump into it. We're going to start dealing with what galvanic cells are, what standard condition. I hope that you're not answering as well. I know that, and I'm not sharing.
Yeah, that's
so
rude.
I'm hoping that's the case. But guys, galvanic cells, there's a couple of things that you need to know about galvanic cells. Galvanic cells do something very specific. They take chemical energy or chemical potential energy. And what they do is they take this chemical potential energy and they change it into something a little bit more useful, which is electrical energy. So they change it into electrical energy, and that's hugely useful. A lot of you are saying, well, I don't use galvanic cells. Guys, you do. Your cell phone, hopefully one of your tablets, one a day.
He looks a bit...
Yeah, well, I'm jealous of that tablet, okay? I want it. So, guys, if you don't want it, I've told Samsung I'm going to take it
Galaxy
for myself.
10, guys, come on, enter.
It's good. I'm going to take it if you don't. Okay, so we started talking about galvanic cells. It told me that Vanessa set up a galvanic cell, so now we know what a galvanic cell is, but under standard conditions, guys. Okay, now these standard conditions, with reference to the cell, there's 3 standard conditions, but only 2 that apply here. The first and most important standard condition is 25 degrees Celsius. Guys, that is put inside textbooks as room temperature. Now, guys on the Houfeld here.
At the moment, it's like 35 degrees.
Yeah, guys, it's a little bit hotter than 25 degrees. Okay, so the galvanic cell wouldn't work very well under these conditions. You wouldn't get the voltage that you expect. Okay, so 25 degrees is standard temperature. Now, another condition which is hugely important to this cell is 1 mole per decimeter cubed. That's the concentration. Okay, so 1 mole per decimeter cubed is the concentration that Vanessa would need to have for a silver nitrate and for a copper sulfate. Anything other than that, she won't get the volts that she expects. Now, there is a third standard condition, but guys, if you put it down, you're not going to get your marks, because they say with reference to the cell. That third standard condition is 1 atmosphere of pressure, or 101.3 kilopascals. Now, that doesn't apply to this particular experiment because there are no gaseous reactants. There's a metal, and there's 2 solutions. And then there's another metal. Guys, there are no gases. Gases don't count. Pressure doesn't count. So these are the most important standard conditions. Okay, now this next part is a little bit of a tricky one, because lots of people said, don't worry, I don't have to learn moles. Moles is grade 11. Guys, nonsense. You still have to know your basic chemistry, and moles are going to come back to bite you if you don't study them.
Yep.
Now, lucky for us, it's a very simple calculation. Okay, so it says what mass of AgNO3, so we've got a mass of AgNO3 must be dissolved to make up a solution of volume 275 centimeters cubed to achieve the standard condition. Okay, now they've been very sneaky over here. They said, oh, to achieve the standard condition, which means 1 mole per decimeter cubed. They're actually giving me the concentration. So they're telling me the concentration here of 1 mole per decimeter cubed. Okay, so we've been given a concentration, we've been given a volume. Okay, that's really nice, but they want the mass. There's no formula with C and V and the mass. But what we can do is we can refer to this equation here that says C is equal to N over V. Now, lots of metrics out there. So, okay, well, now I can manipulate that and then substitute. Guys, please don't fall into that trap. Substitute and then manipulate. Because even if you've used the wrong values, it shows your examiner, your markers, and these are the most important people for the rest of the year in your life. Okay, substitute first. You might get your marks for doing the right methodology. You've used the value, fantastic. They know that you're trying to use the formula correctly. If you mess up this equation or you mangle it up in the incorrect way and then substitute, 0 marks. Nothing for you. No doctor, no lawyer, no engineer. Okay, so what we've got to do is substitute the values and hopefully something good comes out of this. But we've got to be careful. We know that the concentration is 1. Okay. But what about, okay, the number of moles we want, which is good, because we're going to turn that into a mass. So that's my number of moles. Now, my volume. This is very nasty. They've changed our volume into centimeters cubed, and we need it in decimeters cubed. So what you do, divide by 1,000, and what we're going to find is 0.275 decimeters cubed. Okay, so now I hope that you don't need a calculator for this next one, because it's 1 times 0.275. So that's really cool. Now I've got my number of moles. So my number of moles, okay, so my moles is equal to, or my moles are equal to 0.275 moles of my material. But we're not done yet. Okay, I know this is a little bit nasty, but we are not done yet. What we've got to do now is I've got to change moles into mass. Okay. Next equation, and this is why you needed to study moles, guys. I've got to take these moles and I've got to change them now into mass. And the equation that allows me to do that is N is equal to my mass of my material, which I'm after, over the relative molar mass of my formula. Now we know that the number of moles is equal to 0.275. But what about my relative molar mass? Now, I'm a little bit worried when I see some people doing this because they say, this is such an easy calculation. Then they start doing something really strange. They start to mess up my relative molar mass. And guys, it's as simple as this. Add up the masses. Please don't multiply them or divide them or do something fancy. You've just got to add them up. So I take 108 for silver off your table. Okay, that's the mass number. Plus 14 for my nitrogen. Plus 3 oxygens at 16 each. Okay, now my brain's not that advanced, so I'm going to have to do this on my handy calculator. Okay, so what am I going to do? So first let's find that mass, that relative mass over there. So I've got 1. That's not 1. Okay, there we go. Hold on, we're busy drawing all over our calculator. That's not what we wanted.
Not cool.
Okay, there we go. So 108. So 108. Add 14. There we go. So we're going to add 14 to that, plus 3 times 16. So 16, there we go. We're going to close up our brackets. We know that 1 mole of silver nitrate is going to have a mass of 170. Now, we've got to multiply it across to simplify it, multiply it across by n. So I'm going to multiply that by, we don't have to double multiply it, so 0.275, and that should be the mass of my silver nitrate, 46.75, and that's my mass. So my mass is 46.75, and don't forget your units, please. There's a mark to be lost every time you leave off a unit for your final answers. So that tells me how many grams of silver nitrate would need to be dissolved in that much solution. Okay, So continuing on our question, it says, what will Vanitha observe happening with the light bulb? Okay, so it says use a calculation. Okay, now you say, well, this seems a little bit simple. You know, what will she observe happening with the light bulb? Well, a light bulb shines. Now it says use a calculation to support your answer. What possible calculation could I use which involves voltage and galvanic cells? Well, guys, this is really not too difficult. What I've got to do is I've got to take my standard potential for the cell and compare it with the 1.1 volts which my bulb needs. So the way that I do this is I've got to say cathode minus anode. My cathode potential minus my anode potential. So I take my cathode potential minus my anode, but the problem is I don't know which one's my cathode. However, I do know that my cathode is where reduction takes place. Okay, so reduction minus my oxidation reaction. And that I'm going to find on my redox table. So let's find my redox table. There we go. We've got a redox table. This is the best cheat sheet ever. And we're going to try and find out what's going on here. Now, I just want to show you some really important and potentially confusing things inside this sheet over here. Okay, now a lot of you say, okay, well, what do I circle? Okay, I see copper all over the place. I see copper plus. I see copper 2 plus. I see copper 2 plus in 2 places. Oh, now that's really confusing. Also, I see copper metal over there. What do I do? Okay, now I'm going to show you exactly what to do, so don't panic, breathe. We're going to work on this together. Now, what I'm going to see on the other side there, I see Ag+, that's what I need, and some Ag metal. If you're sitting there with a redox table, you should have circled exactly the same things with us. I noticed that some of them in some of the distributions don't have the second copper reaction, but not to worry, guys. You'll notice that there's something which really helps you on the sides of these tables. You'll see on the left, I see an arrow which points down, and on the right, I see an arrow which points up. Guys, these arrows are the best thing ever, because those arrows will be there tomorrow giving you the answers, and I'm going to show you how to use this. Okay, so now what I've got to do is I've got to say, okay, which is the best oxidizing and the best reducing agent for the job? Now you might say, okay, well, I don't even know what those words mean. Guys, it's as simple as this. On the left, I've got 3 chemicals which I can choose from. The arrow tells you which one's the best. So between copper 2 plus again, and Ag+, Ag+ is the best chemical for the job. That's fantastic. That means that that is going to react. Now what we see is that that is going to react by going across the page and forming some silver. Guys, if you read the reaction in the direction that I've drawn with the yellow arrow, you'll notice that electrons are on the left-hand side of the reaction. That means that this is my reduction reaction. That's quite nice. So that's the reduction reaction. But what about on the right-hand side? Now I've got to choose, and I'm going to pick a different color. How about some blue? Let's use blue. So I've got to choose between silver and copper as the best reactant for the job. How do I choose? Once again, look at the arrow on the side. The arrow is pointing up, so the furthest up to the top, here we go, copper is the best chemical for the job. Now the way that I read this is you start where you've chosen the chemical. So I'm going to start from copper metal and then read it the other way around. So that is my oxidation reaction. That's really nice because that tells me that this is my oxidation reaction. And what we're going to find over there is we're going to change what we're doing over here. Now, what's going to happen is I'm going to subtract these 2 values. Which one minus which one? Okay. Now, if you remember, I'm going to take my reduction. I'm going to minus the oxidation. How am I going to do that? Well, we're going to use these values over here. So I'm going to say 0,8 minus 0,34. And that's going to be my potential. Okay, so let's do exactly that. So 0,8, which is positive, so positive 0,8. And here's just another pro tip, guys. Keep them in brackets, because there's a minus waiting to ruin your day. Positive 0.34. Okay, so if I do all of that inside my calculator, what am I going to get? Okay, so what you'll find is 0,46, positive 0,46. Okay, now that's no big deal. That voltage doesn't tell me anything about the light bulb. However, the light bulb was marked with 1.1 volts. This is not enough. So Vanitha's experiment was not successful in one way. She didn't manage to light up the light bulb because the light bulb needed more than double this voltage. So the light bulb would not shine brightly, if at all. So that's what you can say, is that the light bulb, if it does shine, it shines very dimly or not at all, because the voltage is not enough. That light bulb needs 1.1 volts, and this voltage under standard conditions is 0.46 volts. Not enough. Okay, so state 2 reasons for using the apparatus labeled B in the diagram. So let's go back to my diagram, and let's see what B was. So right at the beginning, I said that there was this really strange thing over here, B, which is kind of like U-shapes. And oddly enough, this piece of apparatus is actually called a YouTube. Now, this has got nothing to do with the online video service, okay?
Imagine.
Okay, well, absolutely. You can't watch anything funny on this. There are no squirrels which are doing surfing or anything like that. Okay, so this YouTube contains a solution inside. Now, that solution is made up of ions. And for this reason, it's going to connect the two. So let's see what we can use the YouTube for. Okay, apart from videos, which is online. Okay, now the first thing which it does is it connects the 2 parts of the cell. So it completes the circuit. Okay, so it completes the circuit. It allows for the charge to flow all the way around the circuit. So it completes the circuit. And that's really important. What else does it do? Now this is the really important thing. And this has got a very fancy word attached to it. If you're manufacturing ions in one compartment and you're destroying ions in the other, ions need to flow to replace them. This is called quenching. Okay, just like you quench your thirst, if you're thirsty for ions, you're going to grab ions out of the salt bridge. So this is quenches the ions. It quenches ions. So it means that any ions which are missing, it replaces them just the same way that a drink quenches your thirst. Okay, so it quenches ions or it remains neutral by supplying these ions. So it's got 2 very important uses. Okay. Now what we're going to start doing is we're going to start to get into the actual redox. It says write down a balanced chemical equation for the reaction taking place in the cell. Now let's go back to my redox and let's find out how to get them off that table onto your page to get your marks. Okay, so here we go. We've got our 2 reactions. So let's go through how to choose the correct one. Okay, so step 1 is to always find these chemicals. I call them species. So find the species. So this is your game park, and you've got to find the species inside the game park. I found 2 copper species and 1 silver species as ions. There's a very big difference between Cu2 plus and Cu. One is a blue ion, one is a brown metal. Ag plus is a clear ion, Ag metal is a valuable metal. Okay, so there's a very big difference. You've got to be very specific. Now, some textbooks will tell you to circle the entire reaction. Guys, it's going to put you at a disadvantage. Don't circle the entire reaction, just circle what you have. I have Cu2 plus. I have copper metal. So circle them. I have Ag plus and I have Ag metal. So what I can do now is I can choose the best one using the arrows. So let's just remind ourselves, I chose Ag plus because it was at the bottom. I chose copper metal because it was at the top. Now let's discuss that C method that was being talked about. Now, who was it suggesting the C method, or is it way up the page?
No. Let me just quickly find it for you.
Okay.
Go carry on speaking.
Okay, so now what the C method actually does is it gives you a way of figuring out which direction the reaction goes. But guys, use this with caution, because it only works with galvanic or electrochemical cells which are spontaneous. Okay, anything else doesn't work at all. So what you do is you start at the top right with your one which you chose. You're going to draw a C through the 2 reactions. And that gives you the direction of the reactions. Now, I prefer a slightly more standard approach. What I choose is I say, okay, I chose the copper. I'm just going to write the reaction starting with copper and go across. I'm going to start this other reaction with Ag plus because I chose it, and then move across. So let's see what comes out when I write this all down.
The learner's name is Evangelist.
Okay, so Evangelist, guys, the C method does actually work, but only for galvanic reactions. Okay, so be super, super careful. Okay, so those 2 reactions which we said, starting with the copper. If you're using the C method, fine. Okay, now you only write one direction of arrow because we know which direction the reaction is going, and that makes Cu 2 plus 2 electrons if you wrote it out in the correct way. It's a good idea to label it. Guys, that is clearly oxidation taking place because the electrons are coming out. What happens to silver? Guys, silver is a good oxidizing agent and therefore undergoes reduction to silver metal. Okay, and that is my reduction half reaction. Okay, so now what they're expecting us to do is to add them together, get my whole cell reaction. Okay, now what happens over here is I know that the electrons don't match up in these two reactions, so something really important to do in my next step is to balance the electrons. I need to have 2 electrons in both reactions before I can cancel those electrons out. Now all that's left to do, and this is the easy part, guys, is I need to put in, there we go, so that's copper plus 2 Ag plus, and that goes to form copper 2 plus 2 Ag. Now, just taking it one step further, you can add in your other anions, but that's probably not what they're looking for. And that ties up that question. Now, unfortunately, we're not going to get a full time to march through the next question, but what I'm going to do is I'm going to set the ball in motion and hopefully carry on the conversation online. Now, this was an absolute stinker of a question. It was amazing how difficult this was and how much it caught people. Okay, so now it said, in the motor industry, delicate finishes on luxury cars are often completed by installing chrome-plated components. So that means that they have got a layer of chrome metal. It says that the components are electroplated by using an electrolyte containing Cr3 plus ions, so chromium ions. The anode is made from pure chromium so that you can make more Cr3 plus. And it says the cathode is made from the component, so that's where reduction takes place to make the chromium metal. Now it says for a deposit of 0.1 moles of chromium, okay, the metal of the component, to complete the finish, I put a current of 0.8 amps through the circuit. Okay, now I've got current. This is kind of weird. All of a sudden now there's physics involved in your chemistry. Now it says it needs to be passed through a solution containing the chromium ions, which are 3 plus. We have to calculate the total time it will take the 0.1 moles of chromium metal to deposit on the component being electroplated. Now guys, here's a little bit of a hint. They've given us Avogadro's number. Now since we've only got a minute or so to go through this, what I'm going to do is I'm going to give you a bit of a hint that they're actually looking for the ratio of electrons to chromium ions. Now you're trying to make 0.01 moles of chromium metal, but I know that it takes 3 electrons for every 1 mole of chromium 3 plus. So you have a ratio here of 1 mole to 3 electrons. So that means that the electrons are present in an amount of 0.3 moles. Okay, now guys, I'm going to lay out the rest of the question. We're not going to get time, but what I'm going to do is I'm going to give you a little bit of a shove in the right direction. You have to change the number of moles of electrons into the number of electrons, okay, by using Avogadro's number. Then you've got to change that into the amount of charge, and eventually from that you can figure out the time. So there's several steps in this, and that's a lot of marks. It's 6 marks. Okay guys, that's all that we've got time for.
Thanks, Phil. I'm quickly going to announce the Curio winner, and that is Bandile Misimanga. So congratulations, Bandile Misimanga. Good luck, IEB Matrix. Study hard, work hard. Good luck for chemistry tomorrow. That's all from Phil and myself. Have a good evening, and thumbs up from here at Mindset. Cheers.